Okay, so we can put halogens on those alpha positions, but we really can put lots of different electrophiles, alpha to the carbonyl, if we make those enolates and treat them with electrophiles. So again, lithium diisopropylamine, an extremely strong base. It's going to produce a different enolate, so we treat that with one. It's going to produce the kinetic enolate. So that would look something like this. And again, remember, the negative charge, the electrons, are distributed between this carbon and that oxygen. Versus if we treat it with something like potassium terbutoxide, a weaker base, that is going to promote an equilibrium with the more stable enolate, the thermodynamic enolate. So essentially, if we have different bases, that's going to form different enolates, and those enolates will make different products as well. So what do we have here? We have an electrophile that's going to add to this position. So after we add reagent 1, we're going to add reagent 2. And that reagent 2 will be added to this position. What else? We have our thermodynamic enolate. We add our electrophile to that. That is going to add the electrophile to the more substituted position. And that more substituted position, which was a single stereocenter here, now this is this lone pair. What kind of orbital is that lone pair in? This kind of goes back to things that we actually talked about back in chapter 16. So pretty long time ago. But that is conjugated with the pi bond, so it must be in a p orbital, which means this is a trigonal planar stereocenter where it used to be tetrahedral, and this used to be a defined stereocenter. But now that we've added the electrophile and planarized that stereocenter, we now have racemized that stereocenter. So that electrophile would have added to both the top and bottom of that position. So what did we just see here? Well, the blanks that come under this in the course packet, blank produces the blank enolate because deprotonation is faster. Fast means kinetic, right? The fastest thing happens because it's the lowest energy of activation, the fastest rate. LDA produces the kinetic enolate. So this is the more sterically accessible position. It happens faster. LDA produces the kinetic enolate because deprotonation is faster. Potassium terbutoxide produces the thermodynamic enolate, this one, because deprotonation is in equilibrium. And when something is in an equilibrium, it is going to settle into the most stable option. And then the next thing that it says is if a stereocenter is present, formation of the enolate. So we form the enolate right here. Even if we just picked up a proton, so even if we just reprotonate that, this stereocenter is ruined. So if this was a wedge to start out, if we make the enolate and then we add an H plus to that, it's going to change that from being a wedge to being a mixture of enantiomers. So if a stereocenter is present, formation of the enolate blanks the stereocenter. It racemizes the stereocenter because the electrons of the enolate are localized in a p orbital. So that's what we see for those blanks right there. And the next thing that's underlined says alkyl halides can be used to directly alkylate enolates and enolate equivalents in a moment. So we make a new carbon-carbon bond to our enolate. Well, we're going to deprotonate to form the enolate. Then we will add our alkyl halide. So again, this comes right below the statement that says alkyl halides can be used to directly alkylate enolates and enolate equivalents. Alkylate is a fancy way of saying adding some carbons to it, right? Specifically sp3 carbons. So what does that look like? Well, if we treated this molecule with LDA, what does that make? If we then treat what we had there with that molecule, what does that make? So go ahead and fill in the blanks here. Take a minute to do that. Pause the video, do that, then come back. Boom, crushed it. So yeah, this is going to form the enolate. We can only form the enolate on this side, right? Because there are no hydrogens attached there. So we treat that with 1. That makes the enolate that looks like that. This enolate then will react with 2 in an SN2 type reaction, or in an SN2 reaction. And that will produce the alkylated product. So we had 3 carbons in our alkyl halide. We've added 3 carbons to our product. And that is about that. So this is another great way to make carbon-carbon bonds. And we're going to go through some examples of this very soon.